Hey, Mike, you see and hear us okay in Johnson City?
I do.
Thank you.
So where we left off, whenever the last time we was here, is I was working this problem, 12, I think it was 12:14 was where we was at, and I just want to remind you one thing here, and then I'll finish the problem. But we talked about finite, and I told you I would use the word discrete probability model, and it's all about the sample space. And so when we think about finite or discrete, and I'm going to use those words interchangeably, and what we're talking about is that the sample space, remember the collection of all the possible outcomes from our random phenomenon, it means you have a finite sample space. What that means to us is, there's 4 things in your sample space, or 10, or 12, or 20. The point is you can write them down and we can stop. And that problem, the reason I'm bringing this up, because this problem 12:14 that we were doing on page 288, that's your typical finite discrete probability model. And the question, the way all this is set up, it says, choose an adult age 18 or over in the United States at random and ask how many cups of coffee do you drink on average per day. And so I'm going to do this. The sample space in this probability model is, it was either 0, average, 1, 2, 3, and they grouped 4 or more together. You'll notice your sample space has 5 things in it. That's finite, right? I wrote them all down and I stopped, so that's the way I want you to think about that, is that this is definitely finite. I'm just reviewing just a second, right? Okay? And I think where we ended up is, I'm pretty sure we did part A where it says verify this is a valid finite probability model. I just verified that it's a finite probability model. And then when they say valid or legitimate, when I look here, there's 2 things I always got to know. When you've got the sample space listed like in that table, and you have a probability assigned to each one of them, every probability needs to be a number bigger than or equal to 0, less than or equal to 1, right? And when I add all 5 of those probabilities up, they're supposed to add to 1. Okay? That's the 2 things I'm thinking about to see that it's valid or legitimate. And then I'm pretty sure we did part B in class. And so where I'm at is, I'm in part C. It says, express the event, have at least 1 cup of coffee on an average day in terms of X. Well, remember, X is the average number of cups of coffee per day. And what's at least 1 mean? Now look, I'm not like the English major guy and shit like that with teaching you English. But when somebody tells me at least some number, it means that number or more. So right there is a way for me to write down in terms of X, what does at least 1 mean? That means X is bigger than or equal to 1. Correct? Everybody okay with that, right? So I want to give you the other side of this. At least a number always means that number or more. Some of the problems will ask you for at most some number. At most a number means that number or less. Okay? So that's the way I think about it, at least. And then they're going to ask me, I'm going to give you, obviously, the next part of this question is going to be, what's the probability that X is bigger than or equal to 1? Which means, what's the probability that the person you chose had at least 1 cup of coffee on average per day? Right? That one person you chose. Now, there's 2 ways to do this. Depending on what we remember from last Thursday, 2 Thursdays ago, about the little rules, probability rules, I could do this. Remember, the probability that something occurs is equal to 1 minus the probability it doesn't occur. Well, the only one you're missing here when you're looking at X being bigger than or equal to 1 is X being 0, right? So I can go at it this way and say, well, that's equal to 1 minus the probability that they had a 0 average cup of coffee per day is 0.36. So it looks to me like this probability is 0.64. Okay? Okay, so I'm going to do it like this also. That's one way. And that's one way if you remember, I can't remember what, I think it's rule 4 that I've written down. Let's say you don't remember that rule. My question is can we still do this? What does it mean? In other words, what I want to know is, this is your event, that x is bigger than or equal to 1. What outcomes make up that event? Well, it could be 1, 2, 3, 4 more, right? So I could be looking at the probability that x is 1 plus the probability that x is 2 plus the probability that the average is 3 plus the probability that x is equal to 4 or more. Well, if you'll notice, all I'm doing is adding up the outcomes that make up that event at least 1. So I would add together 0.26 plus 0.19 plus 0.08 plus 0.11. My answer should be, well, hell, it had to be the same way as I did the other. I'm either adding them up directly or I'm taking 1 minus the one that's not there. Either one is fine. If you don't remember that little rule that I showed you on the top here, that bigger than or equal to 1 is 1 minus being 0, then we just add the ones up that make up my event and we just go on about our business. Okay? To me, that's a typical finite discrete probability model. What does that mean to me? I have a nice little table. One row lists the outcomes, and one row lists the next row lists the probabilities. And then what do? Whatever event somebody wants me to talk about, I take the outcomes and make that up, and I add their probabilities together. That's exactly what I did. If you go back and look at Part B from 2 Thursdays ago, that's exactly what I did there. I added up the outcomes that made up that event, those probabilities. For the things that me and you do, they don't get any simpler than a finite discrete probability model. So then, it comes to our second type of probability model, which is a continuous probability model. And what makes this different from the finite case is your sample space in other words, your possible outcomes, they're not finite, right? So, what is it? The sample space is an interval of outcomes. In other words, there's an infinite number of them, and they're uncountable. I have no shot at writing them down whatsoever. Okay? Now, my thought about this is the one I want to start with is this. I would like to have some kind of random number generator, and I would like to choose any number between 0 and 1. And I'll let 1 and I'll let you choose 0, but I want to choose a number between 0 and 1. My sample space here, in other words, what outcomes make up this event? Well, any number between 0 and 1 is a possible outcome, so I can't even list it. All I can do is say, okay, my sample space here is this S, it's all numbers. Between and including 0 and 1. Alright? I got no shot at writing them down. There's an infinite number of them, and it's actually, if you think about it, I know we're not math people, but I'm on the number line here, and I'm looking at all numbers between 0 and 1. That's an interval of outcomes, right? So this is a continuous probability model. And what else I'd like to do, I'd like to call Y. Notice I'm using this capital letter Y at the end of the alphabet. I'd like to call it the random number generator. So then the question is, with this continuous probability model, there's always supposed to be two parts. There's supposed to be a sample space, and then there's supposed to be a way for us to assign probabilities to events or outcomes. The question is how do we assign probabilities to the following, for example? See this right here? That's an event. The event is that when you generated a random number between 0 and 1, you generated one that was bigger than or equal to 0.3 and less than or equal to 0.7. The event has so many things in it, you notice I can't write them down in a nice, just list them either, right? So the reason I'm saying this and I'm writing it like this, here's the point, all right? There's no way in hell that we're going to figure out, okay, what's the probability of every outcome in that event and add them up like you do in the finite case. You know, like that problem I just did where I added the pieces together. We can't do that. So what we're going to do is, we're going to back up to chapter 3. We're going to use areas under density curves. That's going to be our answer to that problem. Well, what's our favorite density curves? I'm in chapter 3. It's always the one I draw, right? Symmetric, single peaked, and bell shaped. My favorite density curves are always normal curves. Yeah. So we're getting ready to revisit that part of chapter 3. Remember, a density curve, what makes it a density curve has area 1 underneath it, and when I was in chapter 3, I said, oh yeah, every density curve I draw you, what makes it a density curve is it has total area 1 that represented 100% of the observations, right? Or a proportion of 1. Alright, so what you guys got to get used to now, anywhere I can calculate a percentage or a proportion, I can calculate a probability. How's my probability defined in this chapter? It's defined in terms of the proportion of times your outcome would show up in a very long series of trials, right? So anywhere I can calculate a percentage or proportion, I can calculate a probability. The notation is going to look exactly the same. Everything's going to look exactly the same because that density curve having area 1 underneath of it is corresponding to probability 1. If I was in chapter 3, I'd have wrote proportion 1. Alright. Now, here's what I want to do. I want to find us a problem that looks very, very similar to what we were doing in chapter 3. And what I'm expecting out of you folks is, there's an example here, 12.9. I would expect it for you to read that when you get to the house. Right? I'm not going to go through that with you. You can read it and be fine. Example 12.9. You read that one for me. Please. There's a term in there about like a uniform distribution that you need to look at. And you can look at it by yourself without me. What I'm thinking is the following. We will use normal curves. It's our favorites. In other words, back in chapter 3, those normal distributions are, turns out, with the right wording, are continuous probability model. All it changes is how the wording is done. I have one stuck in my head. There was one we worked with back in chapter 3, and it was like the heights of young women aged 20 to 29. It turns out they had like a mean of 64 and a standard deviation of 2.6 or something. I mean, I might be off a little bit, but that sounds familiar to you, right? So it turns out that the heights of young women, they follow that normal distribution, right? Where the mean is centered at 64 and the standard deviation was 2.3 or 2.4. The difference is, in chapter 3, we were looking at all the young women at one time. Right? And so we had that normal distribution to describe that variable. In what chapter is this? In chapter 12, what we do is, bless you, how do we turn it into a probability question is, we choose one young woman at random, and we measure her height. We set her aside. We choose another one. We measure her height. We choose another one. In other words, I'm taking an SRS of size 1, and I'm going to choose one, and I'm going to choose the next one, and I'm going to keep track of all their heights. Don't I eventually get them all? In other words, don't I get the exact same normal distribution? Instead of in chapter 3 looking at all of them at one time, or in chapter 12 choosing one at a time and just keep that choice going until I get them all. Is it not the same normal distribution? And the answer is, yeah, it is. Okay? So the only difference is the wording. And I'm going to point the wording out to you when I work this problem here. The example I would like to work for us is, what about 1217? Right, so this is your typical continuous probability model. I am on page 293. I want to point out to you what separates this from, let's say, a problem in chapter 3. And it says the medical college admissions test, the normal distribution with mean 499.6 and standard deviation sigma equal 10.4 is a good description of the total scores on the MCAT test. They just told you had a normal distribution. The mean is 499.6, and the standard deviation is 10.4. I want to remind you, there is your mu, there is your sigma. That's my notation, right? I always give you mu and then sigma. Normal distribution is telling me where you're centered. It says, this is a continuous probability model for a score of a randomly chosen student. When you see a randomly chosen whatever, here comes the probability questions. It says, call the score of a randomly chosen student X for short. So X is the score of a randomly chosen student. If you want me to put it in fancy language for you, it's a SRS of size. Oh, hell, you number all the students, you give them all labels, and then we pick one out at random, right? So you choose you want to think about a randomly chosen student, you're choosing an SRS of size 1. Now, I'm going to change one more color here, because as soon as I see this, what your question is going to be about, now all of a sudden we're going to start talking about probability. Not the percentage here, not the proportion there, like we would have done in chapter 3, but now you're going to choose one at random, and now I want to know the probability of something about this one you chose. And so, part A says, write the event. The student chosen has a score of 510 or higher in terms of X. What does it mean to be 510 or higher? I'm translating it into symbols for you like I would have done in chapter 3. So that means you want X, the score of that randomly chosen student, to be 510 or higher. That means greater than or equal to 510. Right? That's all they want for that part. And then in part B they want the following. In part B, we want the probability. Big capital P stands for percentage, proportion, probability of that event. So I want the probability that that randomly chosen student score is 510 or higher. So that x is bigger than or 510. Now here's what I got on my head. This looks a lot like, to me, something I would have wrote down in chapter 3. You know, that x was bigger than this or less than that, bigger than or equal to this, or between here and there. I've got that on my mind, and I have why am I circling that shit? Okay, so I don't care if it's a probability question or not now. What I need to do is I need to find the area under a normal curve, right? Because I'm looking at a normal distribution. So, from here on down, it's going to look like I was doing what we've done before. I'm going to draw you that normal distribution. It's centered at I'm interested in the value in my question. X is bigger than or equal to 510. Which way would you like the shade? Right? I want that area from 510 greater. If I was in chapter 3, what would I do now? Well, I might ask you that dumb question. Are you 1, 2, or 3 standard deviations away to see if we can talk about 68, 95, 99.7? But we're not. So then how do I actually find that area that I have highlighted there in blue? What's our technique here? Our technique is to standardize. You standardize by calculating a z-score, and the z-score is always an x minus a mu over a sigma. Right? That's your standardized value. Kind of reviewing with you. I had warned you chapter 3 would come back to us. Here it is. So the value I want to standardize is this 510. So I'm going to take 510. I'm going to subtract off your mean, that 499.6. And I'm going to divide by your standard deviation, which is 10.4. Somebody's going to give me a calculator and tell me what this number is here, please. Shit, it's 1. Really? The 1? I should have used the 68, 95, 99.7. It's telling me that 510 is 1 standard deviation greater than the mean. I'm going to play like this is not exactly 1. How would I do this if it's not exactly 1? I would do that. Okay? And then what does this do for me? It takes me to the standard normal distribution. The mean of this guy is 0, and you just got a z-score of 1. And I still want this area to the right. I want to be able to use that table A and all that stuff. That's the reason I'm doing this, right? I want an exact answer here. And so this is where you would pull up table A. I would go to the row 1.0 and the column, because that's actually 1.00, correct? Now, you guys didn't want to play along with the calculator, so it's okay. But I do have that table here somewhere, it seems like. And my table is right there. So this is your table A, right? This is the one that I gave you. And I'm looking for the 1.0 row, which is right here, and I want the 0.00 column, which is the very first column. So everybody follow. I'm in this row here, 1.0, the 0.00 column, and I'm reading 0.8413 there. So what it's telling me is that this area right here is 0.8413. You should just stop me anytime you want. It's telling me this area here is 0.8413. Remember, the table always tells me to the left. In this case, I want to the right. Remember, the total area, the total probability, the total proportion underneath the curve is 1. So I'm going to take 1 minus 0.8413, and I get 0.1587. If I was in chapter 1, I would tell you, okay, the proportion of students that scored 510 or greater is 0.1587. I would tell you the percentage of students that scored greater than or equal to 510 is 15.87, right? In other words, if that's 15.87, that's 0.1587. What's the difference here? They didn't care about the proportion. They didn't care about the percentage. What do they want? They want the probability. What's the probability? So the probability when you choose one student at random that they scored 510 or higher is 0.1587. It's the exact same thing as the proportion we would have calculated in Chapter 3. If you want to turn that probability into a percentage, you can break down 15.87%. Let me ask you this. Does all this look familiar maybe a little bit? It should. This is Chapter 3. At this point from there, right, from here down, the z-score standardizing, going to the standard normal, writing down the table, all that stuff, that's exactly what I did. The only difference is what I have circled in green. The score of a randomly chosen student. What does that turn me into? It's a probability question, so now the answer is going to say, what's the probability? Well, it's 0.1587. Hell, it's the same as the proportion from before. There's no difference in the calculation here. All right? It's all about the language, that's all. Before I find another one of those, because I think those are the ones that maybe have been a while since we talked about them. I'll come back to that in a second, because I want to do another one of the ones where I've got a continuous probability model, and for us, that means we have a normal distribution. All right? Now, a little bit of language here. Get all the language out that we can get out, and my language goes like this. There's something called random variable. Okay? Now, you'll notice that problem 1214 I used a big capital X. Somewhere along the line here, I used a big capital Y, right, for the random number generator. For this one about the scores on the MCAT test, they told me to use a big capital X, and so on and so forth. So my thought is this. I'm on page 293. Okay? There's two definitions here. The first one is a random variable. Oh, I'm not going to write the definition down for you. I'm just going to tell you, okay, this is where it's at. There's a box there. And we want to know this little definition. It says this. A random variable, first off, is a variable whose outcome or whose value is a numerical outcome from a random phenomenon. So this idea of choosing one of these students at random and measuring their test score, that turns that big capital X into a random variable. This idea in 1214 about choosing an 18 or older adult at random and asking them how many cups of coffee on an average day do you have, that turns that capital X into a random variable. The one in the middle here where I use capital Y, where I was saying, okay, let's generate a random number between 0 and 1, that capital Y is a random variable. Why? Because when you start randomly selecting people, or you're generating random numbers, that's a random phenomenon. That outcome is going to be numerical, and so you're looking at a random variable. Okay? One other thing about this. With us, we like to denote capital F, capital Y, and I guess if I had to, capital C. For random variables, this idea of the value coming from a numerical value coming from a random phenomenon, we like capital letters at the end of the alphabet. Why? It's just like, why do we like capital letters at the beginning of the alphabet for events? That's just the notation that people that talk about probability use. Have it. Okay? Now, I got one more definition here. And 2, the probability distribution Now, in that little box, that's the part that's highlighted. That's the part that's in bold, but there's more to it than just probability distribution. It's probability distribution of a random variable. Remember, a random variable is this numerical outcome from a random phenomenon. So, what a probability distribution of a random variable gives you, it gives you two things. It gives you the possible outcomes from your random variable. It gives you the sample space. And how to assign probabilities to those values. I'm hoping that some of this shit sounds familiar, right? So, one, it's going to give you the sample space. What are the possible outcomes? What values can your random variable take? And two, it tells you how to assign probabilities to those values in your sample space. Now, I want to back up all the way to chapter 1. We always speak of the distribution of a variable. What's the distribution of a variable always tells me? It tells me what value my variable can take and how often it takes them, right? Well, what did I do? I stuck the word random on variable from chapter 1. Random variable just means we're looking at some numerical value from a random phenomenon. And instead of just talking about the distribution of a variable, we're speaking of probability distribution. My point is it's the same idea. The variable of distribution tells you what values it can take and how often it takes them. The probability distribution of a random variable tells you the sample space, what values it can take, how to assign probabilities to those values. If I'm assigning probabilities to a value, am I telling you how often something occurs? Or do I need to go back to the beginning of the chapter where that little exercise where we talked about probability tells you how likely something is to happen, right? The higher the probability, the more likely it is to happen. That's what's going on here. I'm just trying to get them connected up for you. Random variable, probability distribution. Still telling you the same thing. It's telling you what values a random variable can take. And in this case, since it's random variable probability distribution, it's how to assign probabilities to the outcomes in your sample space. That's all. Okay? Now, turns out, just like there's two types of probability models, there are two types of random variables. Any thought about what the two types are? Well, there's a finite random variable. What makes the random variable finite? We'll use the language of the book here. It has a finite list of possible outcomes. It means the sample space is finite. 2, continuous. So we can speak of a finite random variable or a continuous random variable. And a continuous random variable takes any value in an interval. In other words, that's just another way of telling you the sample space is an interval of outcomes, like a random number generator, the test on the MCAT score. Now, is this really going to make that big a deal to me that I've called something a random variable and I'm looking at the probability distribution? No, I'd like for you to know what they are. I'd like for you to know that whether we're talking about probability distributions or whatever, you're looking at, you either got a finite type or you've got continuous. Finite means finite list, we just write them down. Continuous means we're looking at an interval of outcomes. That's what's important to you, right? Now, I would like to look at problem 12:19. All right? So I would like to do one more of these continuous random variables. Okay? And so I'm on page 294. (1219) says, a study of 12,000 able-bodied male students at the University of Illinois found that their times for the mile run were approximately normal with a mean of 7.11 and standard deviation 0.74 minutes. So there's something here about these run times of these able-bodied male students that the mean was 7.11 and the standard deviation is 0.74 mu sigma. Right? Just trying to get that stuck in your head. That's the notation. It says, choose a student at random from this group and call his time for the mile Y. Y. Randomly. Chosen. Students. Mile time. Is that all right with everybody? So we're going to pick one at random, and we're going to call whatever the mile time it takes, right? However long it takes to run the mile time, we're going to call that capital Y. In other words, that's a random variable here we're looking at. And it says, part A, is Y a finite or a continuous random variable? What do you think? Is it finite or continuous? You got any shot at writing down all the possible runtimes between 0 and whatever? And the answer is no. You're looking at an interval of outcomes here, right? So we're looking at continuous random variable. Sample space is an interval of outcome, as opposed to being finite. If we can't distinguish between something being finite and something being continuous, then we don't know how to attack it. I'll give you a little heads up here how you know this is not finite. Does anybody see a table with the outcome listed and the probabilities given to you? The answer is no. That's the first thought that makes me start thinking continuous, and then I'm thinking about, okay, so what are the possible runtimes? Well, there's an interval of outcomes here, so this has definitely got to be continuous. Part B says, say in words what the meaning of the probability that the runtime is greater than or equal to 8 minutes is. Folks, I just said it in words, right? Probability that the mile time is 8 minutes or longer. You can say greater than or equal to 8 minutes. Either way is fine, right? The point is I just want to know you know which direction you're looking here. And then it wants to know what is this probability. In other words, they want me to find what's the probability that the runtime Y is at least 8 minutes or longer, 8 minutes or more, greater than or equal to 8. There's more than one way to say the symbols in words. How are we going to do this? You're looking at a continuous random variable. My continuous probability, my probability distribution here is going to be a normal distribution. I'm going to draw it for you. It's going to look like this. It's centered at, remember, that runtime for that normal distribution was 7.11. Here sits my 8, and I want 8 minutes or longer, greater than or equal to 8. 8 or greater than or equal to 8. How do we attack this? This one here will not turn out as clean as the last one. To find that area in blue, to find that proportion, to find that probability, I need this z-score. We need to standardize 8 by subtracting off our mean and dividing by my standard deviation. Did anybody find a calculator yet? It's a little more than 1, but I'm going to need to know better than that.
1.20.
1.20? Yeah, because remember, we always go to 2 decimal places because of the way my table works. So just to remind you, this is telling me that 8 is 1.2 standard deviations, what, greater than the mean? I always want to make sure you check your sign here to make sure you did the subtraction correctly, so we're going to read table 8 correctly, right? That should have been positive because 8 is bigger than 711, just looking at the way things are written out here. So, I draw you the standard normal. You know it's a standard normal because I label it like that. I have a z-score here of 1.20, and I want the area to the right. Unfortunately, the table always tells me the area to the left. Did you give me 1.2? 1.20 looks like, where am I at? I'm here, 0.8849. What do you think? 0.8849? I'm seeing 0.8849. This is 0.8849. I'm going to say it louder. The table always tells you the area to the left or whatever z-score you look up. If I want this one, 1 minus that. And I'm thinking I get 0.1151. Nice. 0.1151. If that's 0.1151, you know I got to flip back here and I got to label this one for you too here. That one is 0.1151. If I was in chapter 3, I would tell you 11.6% of them take 8 minutes or longer, right? But I'm not in chapter 3. I randomly chose. All I got to give everybody is my probability is exactly that area, that proportion, right? My probability here that when I choose one of those students at random, that their mile run time is 8 or more minutes is 0.1151, right? My point is this. From there down, we've done those. What about there's got to be a part C here. Part C says, now they're going to go the other way. They're going to take the English language, we're going to turn them into symbols. Write the event, the student could run a mile in less than 6 minutes in terms of Y, your random variable. What does it mean to be less than 6 minutes? I mean, what's the symbol for less than? Do I include 6 when it says less than 6? And the answer is no. I guess I should ask you, is it going to make any difference in my calculation if I include 6 or not? And the answer is no. All right? So what do? I've got a normal distribution. It's centered at 711. Here sits my 6. And this time, the problem's telling me to shade to your left. So what do we got to do? I need to standardize this guy here again. Yes, I wrote that every time I've used it so you know exactly what the standardized value is, what the z-score is. You're going to take 6 minus 7.11. What'd you get this time, man? I got to get minus 1 point something again. What is it? Negative 1.5, and I'm going to throw the 0 in. Does everybody understand why it's negative? It's negative because the 6 is actually smaller than the 7.11, so you are to the left, right? 1.5 standard deviations. So then we go to our standard normal, and again, the pictures are for me. If you don't need them, don't draw them. But you definitely got to be able to write down what the statement is. You definitely got to be able to find your z-score. You definitely got to know what area you're looking at. And so here, just to remind you in this one, I'm going to be running the table A. I'm going to go to the row that's minus 1.5, and I'm going to go to the column that's 0.00. That's how I get a z-score of minus 1.50. When I do that, if I'm in the minus 1.5 row, 0.00 column, 0.0668. So this is telling me 0.0668. 0.0668. Do I have to do any crazy shit like it's subtracting from 1 or any of that stuff? I already want it to the left. The table told me to the left. That means this is 0.0668. Or if you like, I wanted the probability that your random variable was less than 6 is 0.066. I don't usually give you ones where we're looking at the probability of being between things. You know, you're either to the left or you're to the right. Here's my question. Out of these two problems, this part C is that the runtime was less than 6 minutes. Its probability was 0.0668. The other one, the runtime was what? 8 minutes or longer, greater than or equal to 8. The probability was 0.1151. So this is both of these. You've chosen one of these students at random and you've checked out their runtime, right? And you want to know the probability that it was less than 6, or this one here is 8 or longer. Which one's more likely to happen? That you choose somebody that ran less than 6, or you chose somebody that ran 8 or longer? The one with the higher probability is the one that's more likely to happen, correct? So 8 or longer is more likely you chose one of those than if you chose one that ran less than 6. You're going, they don't even ask me that, buddy. Why are you telling me that? No. I'm looking at 0.0668 versus 0.115. You understand, that's almost double. Yeah, and you're going, dude, you're still looking at point whatever, ever. Well, the thing me and you got to come to an agreement on before I go to the next chapter and we do anything else is every probability that I'm going to produce or you're going to calculate for me is a number between 0 and 1, right? Everyone. You're never going to get a probability of 2.37. It's always going to be a number between 0 and 1. And then the higher the probability, the more likely that outcome is to happen, right? Or that event is to occur. The closer it is to 0 is the less likely it is to happen, right? Because eventually in this class, not next week, but the next one, I'm going to look and the probability all of a sudden shows up to be, let's say, like 0.3127, and I'm going to tell you that's huge. And you're going, but your number is 0.327. How can that be huge? All the numbers I'm looking at are between 0 and 1, right? So I'm looking at like a huge probability. Not a huge number. I understand 0.327 is not huge. But in terms of probability, something that happens 32% of the time, that's pretty likely, right? You understand where I'm going with this? The closer I get to 0, the less likely it is. The closer I get to 1, the more likely it is. If I'm looking at 0.0668 versus 0.1151, the 0.1151 is more likely to happen than the 0.0668, right? So it's more likely that you chose somebody that ran 8 or longer than you chose someone that ran less than 6. I know it's got nothing to do. Nobody asked me that in that problem. I just want to get these numbers in your head that every time I calculate a probability, it's going to be between 0 and 1. Right? The closer you are to 1, the more likely it is. The closer you are to 0, the less likely it is. That's just the way I think about it. I figure if I get you started on those thoughts now, I won't have to break it when I want to tell you that 0.3271 is like a gigantic probability. And it's still 0.3271. All right? That's all I got for this chapter. I mean, I know I talked a lot about it, but to be honest with you, that's all I have. Okay? Now, I do want to go to the next chapter, but I'm only going to do what I want to do. And I've got about 3 thoughts in my head here for this chapter 13, because I can turn this into something very ugly, and I don't want to do that to you, but there are something called general rules of probability. So I can turn this into like a probability class where the notation eats us alive, or we can do the 3 things we need to do that we need out of it. And so I think about it like this. The first thing that chapter does is on page 304, it writes down probability rules and it writes 4 of them. I'm not going to write them down for you because it's the same 4 meaning you talked about in the previous chapter. Remember? Every probability is between 0 and 1. If you take all the outcomes in the sample space and add them together, you get 1. We have the thing about disjoint events, and we have the thing about the probability A does not occur is equal to 1 minus it does occur. Those are the same 4. Nothing new here. Now, the first thing I'm interested in is something called a Venn diagram. So I want to remind you of a couple thoughts here. A and B are disjoint events. Notice I'm using capital letters at the beginning of the alphabet. If they have no outcomes in common. That was the same definition I gave you in the previous chapter, what it meant to say 2 events were disjoint. They didn't have any outcomes, right? There's no overlap between event A and event B. There's no outcome in both of them. All right? That's the first thing. We display relations among several events. Look, I'm quoting you right out of the book here. I'm going to fix this for us. Several events are several is going to be 2. We have a tool using what's called a Venn diagram. So a Venn diagram is a tool for allowing us to have a picture to keep track of the relations between, it says several events, for me it's 2 events. Alright? So here's the way it is. The Venn diagram starts like this. We always draw this rectangle here, and what that rectangle represents is your sample space, all your possible outcomes. Right? So that's the start to the Venn diagram. The first one I want to draw you is, we let little circles inside that rectangle stand for events. So that's the event A. In other words, all the outcomes that make up A are in that little circle. And then there is your event B. Right? So what I've just drawn you in picture form is the big rectangle is your sample space, all your possible outcomes. A is this collection of them over here. B is this collection over here. What I've just drawn you a picture of, A and B are disjoint. That is a Venn diagram representing what it means for these 2 events to be disjoint. How do I know they're disjoint? Can there be an outcome that's in A that's in B? There is no overlap here, right? In other words, they're separated. They're actually disjoint. There's no outcomes that can be in both. Now, more general, what we usually start with in the picture we have for a Venn diagram is this. Again, the big rectangle represents my sample space. So when they're not disjoint, that means they have outcomes in common. There's your event A. There's your event B. These are not disjoint. Right here, whatever's in that little area of your Venn diagram, those are the outcomes in common. right? Those are the ones that are in A and they're in B. Those are the ones we were worried about when we were trying to use that little rule back in the previous chapter about the probability of A or B. You would have counted those twice. Now, I got to write this down for you just because it's here. And we have this general addition rule. Okay? And it goes like this. I have an addition rule for disjoint events, and anytime somebody's talking to you about the addition rule, we're interested in the probability of A or B occurred. Well, if they're disjoint, we know the answer. But if they're not disjoint, see, that's your answer if they're disjoint, because there is no overlap, right? But if they're not disjoint, those are the ones in common. Here, outcomes in common. You got to subtract them out. Now, if you don't mind, I'm going to draw you a Venn diagram here, one where they're not disjoint, and I'm going to show you this little rule there. So remember, my Venn diagram looks like this. There's your A. There's your B. All right? This part right here, just to show you again, this right here is, if you want me to give you like words, there are outcomes in common, that's the A and B part. Now, I'm going to do this. All right? When I see this Venn diagram, there are 4 pieces. There's 4 different little regions. There's 4 different little areas here, right? I'm going to label them like this. There's 1. That's the and. Those are the ones that are in common. There's 2. What outcomes are in 2? They're in A and they're not in B. Right? I'm not going to write that language down. And then there's 3. Right? Those are the ones that are in B, but they're not in A. And then there's a 4. Right? There's 4 little areas, 4 little regions. Those are the ones that are not in A and they're not in B. But they're in your sample space, right? They're not in either one of those events. All right? So, when I think about this little formula with my little numbers there about what little pieces I'm going to add together, what are we talking about with the probability of A or B, right? It could be in A, it could be in B, or it could be in both, right? So I'm thinking about here, that's 1, 2, and 3, right? Those are the little regions that make up the OR. 1, 2, and 3. The ones in common, the ones in 2 not in A, not in B, the 3, the ones in B not in A. Alright? But the problem is when you do A, what little regions make up A? 1 and 2, right? What regions make up B? So what's the problem is you counted the 1 twice, right? And so what are you subtracting out? The center there, 1. Okay, so think about it like this. Regions 1, 2, and 3 are A or B. But if I just added the probability of A plus probability of B, I would have added the 1 twice, right? Because 1 is in both of those. So what do I need to do? I need to subtract out the center there once. Does that seem halfway reasonable about why this is true, whether you're disjoint or you're not disjoint, right? This works every time. Because if you're disjoint, A and B, there's nothing there, right? That's just 0. So I got to get rid of the, when they're not disjoint, I can't count. I'm very concerned about counting this guy right here. The way I've got it written, I'm counting it twice. Right? Regions 1 and 2, and then 1 and 3. Well, hell, 1 showed up twice. I got to subtract that region out once. All right, so to me, there's that nice rule. You know, okay, we can keep track of this, I can keep track of that, go on about my business. If you'll go back and look at your notes from when I started chapter 12, and I did the cards, and I was talking about red cards and kings and queens and all this, and I came up with, okay, I deal you a card. What's the probability you get a red card or a king? I used that formula on you right there. And you're going, so how did you do that? What do you mean you used that formula on me? Well, I'm going to give you this as a little example before I find us another problem here. Suppose I deal a card, standard deck. I want A be that you get a red card, and I want B to be you get a king. I'm going to ask you, are those disjoint or not? Okay, how would I fill in a Venn diagram here? Well, my Venn diagram will look like this. Your sample space consists of all 52 cards. I've got 4 regions to fill in, a 1, 2, 3, and a 4 on the outside there, right? The same 4 I had labeled before. I always want to start with 1 if I can. I want to start in the overlap. How many cards are in the deck that are red and they're kings? Notice my language, red and kings. There are 2, correct? That's the king of hearts and the king of diamonds. Well, let's look at part B. Let's look at event B. How many kings are left over? In other words, how many kings are kings, but they are not red? How many go in that region 3? There are 2. Are we okay? I'm not giving you probabilities. I'm actually telling you how many outcomes are in those events. There's my 4 kings. The ones in the overlap, that's the 2 red ones. The other 2 are your 2 black ones. Now, what about the cards in your deck that are red and they're not kings? That's region 2 there, right? How many cards are we looking at? There's 26 red ones. You already got the 2 red kings in there. There's got to be 24 other red cards. What about region 4 on the outside? How many cards do I have? I got 24 red ones that are not kings. I got 2 red kings, that's 26. I got 2 black kings, that's 28. How many cards are not red and they're not a king? Think about it. That 24 there, those are the ones that are not red and they are not kings. There's 24 black cards that are not kings. How many cards do I have in my sample space here? If I add 24 and 24 and 2 and 2, how many cards do I have? Every card that's possible in your sample space is in one of the little spots, right? Is everybody okay? So that's the simplest one I can give you where I can fill in my little Venn diagram to help me keep track of where in the hell all the cards are, right? So, if I was crazy enough to ask you, what's the probability of A or B? In other words, what's the probability you get a red card or you get a king? Using that little general addition formula, and what I see here is, I would take the probability of A plus the probability of B minus the probability of A and B, the ones in common. What's the probability you get a red card? How many red cards are we looking at? There's 24 plus 2, which is 26 out of 52. How many kings are there? There's the 2 red kings, there's the 2 black kings. And then, how many cards that are red kings? Those are the 2 in the center. If I take 26 over 52 plus 4 over 52 minus 2 over 52, go back and look at your notes. That's the same answer I got before. The Venn diagram helps me keep track of it. The little formula tells me exactly what I need to do. you notice I'm using the number of outcomes in each one, the 26, the 4, and the 2, and I know the sample space has 52 cards in there, so that's going to be my probability. 26 out of 52 plus 4 out of 52 minus 2 out of 52. I apologize if this seems like out of control here. I mean, hell, couldn't I just count it? Yeah, there's 26 red cards, there are 2 black kings, 26 and 2 is 28 out of 52. The formula actually shows you exactly what you're doing here. That's about as simple one as I can come up with for that. I got one more little, I'll come back to that, right? They gotta be like running up there. Okay? Let me do a problem here. Let's do one that's not just cards. Okay, this is how the problems actually will come to us. And I'm on page 306. Please, I want you just to remember that a Venn diagram is a tool for me for keeping track of them, right? The simple one I can give you is keeping track of the cards, okay? If I look at 13.2, this is a place where we would use this, all right? 13.2 says college degrees, page 306. Of all college degrees awarded in the United States, including master's and doctorate degrees, 26% are associates. I'm going to write down what they're telling me. 40% are earned by men. Okay. And then it says 10% are associate's degrees earned by men. So I'm going to do it like this so that there's no question. There's 10% that are associate. Yeah, and I know the book says that are earned by men, but there's 10% of them that are associate, and the degree recipient is men, a man. In other words, that's the overlap. All right? So the problem says after that, make a Venn diagram and use it to answer the following questions. Now notice, this is all in terms of percentages. So the way I see it is there are 2 events. I'm going to call this one here event A, associate. And I'm going to call this one here event, I'm going to use M. I mean, I know I should be using B, but M for men and A for associate seems like the right thing to do. And then, if I'm going to make my Venn diagram, there are going to be little kids up there. I'm sorry, John City. I'm just talking to myself, but we either have young children upstairs running, or we've got these guys from Illinois and they're running a mile around the building. But it's got that young kid sound feet walking, moving. Okay. There's your sample space. Now there's 2 events, right? There's the associates, A, and then M. Now this time I'm not going to put a count like I did with the cards. The best thing I can do is put percentages that fall in each one, right? So what I want to do is I always want to start. Can I label these again for you? That's 1, 2, 3, and outside is 4. Right? I think I'm really consistent with what I did. 1, 2, 3, and 4. I always want to start with 1 if I can. I want to start in the overlap. So what percentage of these degrees are associates and they're earned by men? That is your 10, right? That's the and part. So the 10% goes here. If I've got a percentage, that means that's the probability here is 0.10. Now, let's look at the region 2. The ones that are associates that are not earned by men. Well, what do we know? 26% were associates. You already got 10 in there. What has to be in region 2? Can anybody tell me that it is? Right, the 16 and the 10 make it 26% up that are associates. We didn't count those guys twice, right? What about the region 3 here, area 3? There's supposed to be 40% between 1 and 3. You've already got 10% in 1. There has to be 30 here. Does that make sense to anybody? See, the Venn diagram's a tool for me, not counting that 10% in this one and this one. It gets counted in the middle, and you got to subtract out on the other ones, right? You'll notice 1 and 3 together gives me the 40. The 16 and the 10 gives me the 26, right? I'm looking up here. Notice this is, I got to do this to you again. That's 1 and 2. That's 1 and 3. And actually, that's just 1. What goes in 4? How in the hell do we figure out what goes in 4? What percentage should be in the total sample space? That should be 100%, right? So if I take 30 and 10 is 40, and 16 is 56, what has to go in region 4? I think I actually had that correctly, and that should be 44%, right? I'm going to come over here on the side. How did I get region 4? I took 16 plus 10 plus 30. Oh, I got to do it like the math guy I'm in. I'm sorry. That's what I did, right? I added all those ones together and I subtracted from 100. 30 and 10 and 16 gave me 56 from 144. There's one sure way to know that you got all your shit on here right. If you're doing it in terms of percentages, when you add all 4 of your regions together, they better add to 100%. Right? Because everybody in your sample space has to fall in one of those 4 regions. Right? Now, hell, we didn't even answer the question. I did all that just to fill in the Venn diagram for you. Remember, it's a tool. It stops you from counting stuff twice. If I look at part A here, okay, it says, what percent of all degrees are associate's degrees earned by women? Associate and women. Oh, shit. Wait a minute. All my information was about associates and men. Which ones are the associates that earned by women? Where am I looking? It can't be the 10 or the 30. It's got to be the 16%, right? In other words, in terms of my little region, this is region 2. It's 16%. Remember, it's got to be in associates, and it's got to be earned by women. So that 16% is the percentage of associate's degrees that are earned by women, associates, and women. Part B. What percent of women earn a college degree other than an associate's degree? Ooh. So it's a woman and not. Okay, so I just gave you like my probability math guy thing. There's no problem with me writing women. And not associates means any other degree other than associates. Where am I looking? Folks, that is region 4. That is 44%. I'm going to hold off on part, no, I'll do part C. Okay. Part C says, what percentage of all degrees are earned by women? So it's just women here. Well, I'm going to go back and I'm going to look at my little part here. Which ones are earned by women? In other words, what regions make up earned by women? That is 2 and 4. So what we're going to do, we're going to add together that 16 plus the 44 is 60%. And look, that can't be no shocker to you. Hell, let's go back up here for a second. I'll come right back. What percent were earned by men? 40. What percent is earned by women? Hell, that's all the rest of them. I'm showing you in the Venn diagram that was region 2 and region 4, the 16 and the 44. All of that. Okay? That's how I would use a Venn diagram, and it's a tool for keeping track. And what it does is, and I'm going to say it one more time, it stops me from counting that overlap. You notice, the 10 and the 30 gave me the 40, the 16 and the 10 gave me the 26. When I add all 4 of those together, I get 100%. And I know the thing that always happens, as soon as I give you a homework problem, you guys will come back and you'll have more than 100% on your Venn diagram. That's the reason I keep preaching that to you. Okay? Now, the other thing I want to do is this. I got another definition here, and I want to throw it out there because we need this little thought here. So, A and B are independent. Notice different than disjoint. Okay. Here's my definition in language. If knowing that A occurs, in other words, we know event A occurs, does not change the probability that B occurs. So in other words, you got two different events here. And the term here is independent. Disjoint means they have no outcomes in common, right? Independent means knowing that the event A occurs does not change the probability that B occurs. I can give you two really simple examples of this. Let's say I'm going to flip a coin and I'm going to flip it twice, right? Event A is the first toss of the heads. The event B is the second toss of the heads. So I flip it. All of a sudden the first toss is the heads. Does that change the probability of the next one being a heads? Does that change the probability of B occurring? No, right? That's independent, right? The first toss and the second toss, or the third toss, or whatever, yes? You want something that's not independent, as simple as I can change it for you is, I'm going to deal you two cards. Right? The event A is the first card's a red one. The event B is the second card's a red one. So I've dealt you a card, the event A has occurred, and there's a red card laying on the deck, on the table there, right? Did that change the probability that the next card is red? Yeah. It used to be 26 out of 52. Now it's 25 out of 51. Those are not independent. Make sense? So event A occurs. Does that change the probability that B occurs? The reason we're going to be interested in independent events is because there is a multiplication rule. For independent events. And what we're interested in is the probability of A and B. A occurs and then B occurs. My big dot there is multiplication, right? So if they're independent and you want the probability of A and then B, it's the probability of A times the probability of B. In other words, if I'm going to flip a coin twice, what's the probability I get heads and then heads? It's a half times a half, right? Because they're independent. I add the probability of each one. I can't just do that for dealing you out two cards. They're not independent, right? That's only good for anytime you ask me about and, I'm worried about if my events are independent or not. Anytime you ask me about A or B, I'm worried about my events being disjoint or not. Right? That's what I'm worried about. Now, on Thursday when we come back, I need to do two more things. One of them is this. I just want to get you a little thought. I'm interested in conditional. I don't feel bad about saying this out loud without saying anything about it yet. Conditional probability. And the reason I don't is back in chapter 6, did we talk about conditional distributions? Remember, we talked about conditional distributions, two-way tables, and all that stuff in chapter 6? So, conditional probability, what we're going to be able to do on Thursday is we want to calculate probabilities from a two-way table. And one of them is going to be, just like we did conditional distribution, we're going to calculate conditional probability. Now here's the thing. I already started you tonight with anywhere I could calculate a percentage or proportion, I can turn it into a probability question. What did me and you calculate like crazy out of a two-way table? Marginal distributions, right? Conditional distributions. They were percentages, yes? So anywhere I could do that in a two-way table, I can calculate you probabilities. What's going to change? It's going to be the language. The calculation is going to be the same. So we're going to start with two-way tables, conditional probability, give you some notation, and then I got one other thing to talk about, and then we'll move to the next chapter. Be careful going to the house. We will see you on Thursday.